Hello all and welcome back. So in this video, let us now learn about one more sorting algorithm which is known as insertion sort. Now I'm pretty sure till now you must have coded and understood the bubble and selection sort properly. In insertion sort, we will be again doing the same thing. We will be given an array, right? So let us assume the same number of elements. We have 11, then we have 25. So actually 12. So let me rewrite it. 12, 11, 12, 25, 11. 34, 90, and 22. Now, the whole philosophy of insertion sort you can very easily understand if you have ever played cards in your life. When we used to play cards and we used to receive the cards randomly again, right? What we used to do was, so if I can just help you imagine once, we used to have these cards something like this, right? So something like this, we used to get our cards, everyone. Our whole aim was to sort these cards so that we can use them properly when we play them, right? Now, let's say this is 8, 2, 5, and 10. We used to first pick up 2, okay? We used to first see the 8 only, okay? Then we used to see 2, and we used to shift this 2. Then finally, we used to get something like this. 2 is at right position, 8, 5, and 10. Next, we used to see 5, and we used to make sure that in our mind, this left part used to be a sorted array kind of, right? So we used to make sure that we are inserting. So here actually shifting is happening. We are not doing any sorting or anything. Here we will be maintaining a sub part which is sorted. And once you are moving forward, you will just pick up an element and insert it at the right position. That is all what we are doing. Let me help you visualize after we just dry run this. So in the round one, okay, in the round one, I will just assume that I have 12. In round 2 or past 2, we have 12 and now we got 25. So 25 seems to be fine. See, the very first one, a single element, always sorted. Then I see 25. I am sure that 25, the element which is just one less than 12, one less than 25, which is 12. Okay, index, like index wise, one less than 25. So we can write the index as well. 0, 1, 2, 3, 4, 5. So this time, because 25 is greater than 12, we are all fine. We can just keep it here only. Next, in the round 3, I am going to pick up 11. Now, in my mind, subconsciously, we are maintaining this part as a sorted array, a sorted sublist. I will see where should 11 come. And that is what we used to do. If here we are picking up 5, we used to insert it here, right? So I will first compare it to 25 and I will know that, okay, 25 should shift. Then I will compare to 12, 12 should shift. And finally, I have reached the end. So that means 25 should come somewhere here. Next is 34, seems to be right. Let me write it in a different overall round. So next round will be everyone 34. 34 seems to be right, so we don't have to move anything. Then we have round 5. Okay. In round 5, it is 90. We are picking up the fifth element, that is also fine. 12, 25, 34, 90. Now you will see one thing here when I was on round 4. This part is always sorted. And this part with the leftover one, we try to make sure that each and every element I can insert in my sorted part. Now the last one is 22, which we saw needs to be sorted. The right position of 22 is here, which means 90 should shift, 34 should shift, 25 should shift. So in the final round in round 6, okay, we have something like 11, 12, 22, 25, 34, and 90. And let me write this in a different color to say that we have inserted that. Okay. So that's the whole philosophy, everyone. Now, few things you will see. This has to be done for 6 rounds only. Okay. So running for each and everything, we can actually start from 25 because this first round you will see is redundant, right? So in that way, it has also n minus 1 round. So let me write this as well. First round not required as one element always sorted. Right, everyone? So this thing we have understood that first round is not required because one element we can say it's always sorted. So that means from round 2 to 6, all are required, which means we have to do n minus 1 round. Okay, great. So this all I'm saying because you will have to make sure that you implement this solution completely. Now let me help you to just visualize a little bit more. The way we do it, everyone, is something like this here, right? So in terms of cards, right? Let's say we have these cards. First card is here. Then let's say 6 is inserted. Then 10. And then if 7 is coming, we have to make sure that we make place for 7. And in your life, you must have been doing something like this. So to make sure that where this 4 will get inserted, 1, 2, let's insert 4 here. 5 and 8 will be this way. Okay, great. So let us see this once in our Hacker Earth as well. So let us use these elements only. See, my aim is that I am able to help you visualize each and everything so that you never forget. I have seen many students, they try to remember the code for the sorting algorithm. And I don't want even a single student from this particular course to remember that. That's why I'm making sure that I help you visualize each and everything to try to build the intuition. Okay, let us now run this. See, these are the elements. First one is already sorted, so it is green, right? We begin with the record in position 0 in the sorted position, and we will be moving the record in position 1 in blue. Great. See, processing record in position 1, this one, we will just compare it with 12. So it seems that it is fine. Now I'm picking up 11. So pay attention, everyone. 25 will basically come here to make space for 11. Now 11 will compare with 12. Again, it will make space. Okay, great. Next 34 seems fine. And one thing more you will realize, everyone, that once we have compared this 34 to 25, we don't need to do more comparison. The reason for that is that we know this part is sorted. If 34 is greater than 25, then it will be greater than each and everything here. Okay, because we are taking or keeping a sorted sub array or sub part, right? So now let us move forward, everyone. Let me move this. 34. Now 90 again is also sorted. Now we come to 22. For 22, we will now compare 90, it is bigger, swap. 34, it is bigger, swap. 25, is it bigger? Swap. 22 and 12, no, it is 22 is bigger. No need to check anywhere else. We are all fine and we are sorted. Okay. So pretty sure, everyone, this must have been a lot helpful in understanding how insertion sort works. Again, the basic idea comes from the cards only. That's the best example anyone can give you for insertion sort, because unknowingly we apply insertion sort there. Okay, we have been applying that anytime we play the cards. We are trying to just sort them in our mind in a similar way. So that's why it's the best example for insertion sort. Now again, what you have to do, you have to try to code this algorithm from scratch. These coding algorithms are very important. The reason, you are doing some operations in them, like in this particular implementation you will do this shifting. So if you get an idea about this, it will be helpful in many other codes. Okay, so sorting the algorithm is not a big part. These different techniques which we are doing in everything, that is what we can use going forward when we have to solve some other problem. And that is the reason we study different algorithms. Okay, great, everyone. So let's meet in the next video. Till then, please make sure that you are able to implement the same at your end. And then we are going to discuss the solution as well.